Yeah, so I think we're ready to go whenever you are, Shawna. You're muted. There.
Sorry about that. No, I was just dealing with some last minute internet issues, but I think you can all see and hear me okay. So what I'll do is I'll switch over to the space medicine slides. While I'm doing that, have any questions or any discussion points come from last time when we talked about the future of medicine, engineering tomorrow, engaging in an exponential mindset? And I encourage you to review those slides before Thursday's session. The reason being, you will be asked to put those into practice in groups. We've done it in person, we've done it in Zoom. And basically, that's your turn to put your ideas to work and build on each other's expertise. So come ready to work on Thursday. All I will be doing is helping you out. So I'm going to just share my screen now as we get started here. And then I'll be in full screen mode. So I won't be monitoring questions. So if there's something pressing that comes up, feel free to just unmute, or Kim, if you could
Sure.
draw my attention.
I'll let you know. Yeah.
Great. Okay. So the slides should be loading now. Perfect. About space medicine. Last time I promised you a longer lecture, but that was actually probably my fastest lecture yet. We actually finished ahead of time. So I will warn you, I keep adding to this deck. This is the most comprehensive version of my space medicine talks yet. So we likely will go over unless we don't. I will respect time and we will end at 20 after 3. And feel free to ask questions along the way. So today we're talking about the basics of space medicine as well as challenges as we look to the moon, Mars, and beyond. So I won't reintroduce myself because we did that last time. Just suffice to say that I have a little bit of experience in this area, and we'll talk a little bit more about analog environments later this hour. Here are some of my space medicine affiliations. Again, nothing to memorize, more so you know where I'm coming from when I talk to you about some of the technologies we'll be talking about today. So by the end of today's talk, I want you to have a sense of how the space environment is hazardous to health, how we plan for and mitigate those challenges, the constraints put upon us when it comes to packing for space, how we prepare for space through analog environments on Earth, the value of emerging technologies when it comes to planning for human spaceflight, partially because it's important, partially because it's the technology and the future of medicine class, as well as next generation challenges. So let's get to it. And let's start with a bit of a thought experiment. So I want you to imagine that you as the crew doctor are going to the moon today and you are charged with packing the crew medical kit. So my first question to you is, what are you going to pack with you? So you need an approach. And some might say that you should take a traditional survival framework like Maslow's hierarchy of needs, and starting with the basics for survival, food, shelter, sleep, and then progress to safety. But I would posit this being 2021 and us working virtually, there should be another bottom line added to this. I don't think many of us could live without Wi-Fi these days. But more seriously, to know how we're going to prepare ourselves for space, it needs help to know what we're packing for. So what challenges are unique to the space flight environment? And here's a whole laundry list. And so when we talk about the ways in which space is trying to injure or incapacitate us, we talk about a whole laundry list of problems, everything from increased radiation, which we'll get to a little bit more this hour, to the acceleration, deceleration loads of launch, altered day-night cycles. So when you're on the moon, when you're on the International Space Station, 450 kilometers above the Earth's surface, you're orbiting at a rate such that you're experiencing one sunset, sunrise every 90 minutes, or 60 sunrise, sunset cycles every 24 hours. You need to have your spacecraft protect you from the temperature extremes of the environment. It can be psychologically demanding. The operational schedule of the ISS is planned down to the 5-minute mark. When you're going on an EVA or spacewalk, extravehicular activity, you need to do an oxygen-free breathe, lest you risk decompression sickness. That is, you're going from a higher pressure to a lower pressure. So if you don't wash out all that extra nitrogen, those bubbles come out of solution, lodge in bad places like your brain or heart, potentially kill you. Your resource limited and remote. You need to be confined and protected from the vacuum of space. There's the risk of solar particle events, which we'll talk a little bit more as we talk about radiation. And then there's the risk of everyday lumps and bumps, like trauma, fractures, abrasions, things that you would see on Earth. And of course, the very big one that everyone thinks about when they talk or think about space, which is microgravity. So you may have heard of this known as zero-G, but we're never truly weightless. So the formal term is microgravity. And the summary is that every single bodily system is impacted by the space flight environment. And so that means our bones, without any loading on our axial bones, such as our pelvis and our spines, lose density at a rate of 1.5% per month. And this doesn't plateau off. So it actually ends up reflecting, without countermeasures, without mitigating this, an osteoporotic state that we see in the elderly on Earth, for example. Our muscles, similarly, without being 1G loaded, tend to lose mass without countermeasures. The fluid in our bodies shift upwards. There's no gravity pulling it down. And so this has several effects. When you see those astronauts being carried out of the Soyuz capsule when they land on Earth in a hero's welcome, part of it is pomp and circumstance. Part of it is these astronauts are so decompensated that the valves in their legs just cannot support the Venus return, and the leg pulls downwards, resulting in a state we call orthostatic hypotension or fainting. The other part of it is when we are in 1G, the coordination that provides balance is this fine act between what our eyes see, what the proprioceptors in our nerve endings detect, and what our inner ear and vestibular system detect. And the way that works for those who are uninitiated are these little stones called otoliths bend little hairs in our inner ear called cilia, and then our brain says, oh, it's bending downwards. So that must be a downward 1G force. And now suddenly when you're in 0G, microgravity, those otoliths aren't really matching what your brain perceives. And so there's a mismatch in your perception of balance. And this can actually translate to what we call the space adaptation syndrome or space adaptation sickness, wherein astronauts may get sick, motion sick, even vomit intractably for the first 24 to 72 hours on station. This is why no critical events are planned in the first week up on station to give the astronauts time to acclimate, because let's face it, throwing up on a spacewalk is A, gross, and B, also an asphyxiation risk. The other fun fact about space adaptation syndrome is when Jake Garn first went up on space shuttle, he had the dubious life distinction of being the most sick astronaut ever in the space adaptation period. And so informally, the sickness that an astronauts experience are measured on the Garn scale. This fluid shift predisposes astronauts to kidney stones. We know from Apollo 13 that Fred Hayes actually almost succumbed, or not succumbed, but experienced urosepsis, became very, very sick. And the surprises keep coming. And so here's another graphic speaking specifically to fluids. So we talked a little bit about orthostatic hypotension and how that upward shift leads astronauts to decompensate once back in 1G. The other interesting consequence of this fluid shift is several-fold. So first, there's the aptly named moon phase phenomenon. So here you can see JAXA astronaut Dr. Chaki Mukai, a Japanese astronaut, former mentor and advisor of mine. Here's the 1G state on the left. You can see the normal facial state, and then with that upward fluid shift, you see the puffy, round appearance giving the very aptly spaced name moon face. And so the fluid's shifting upwards. And as a result, astronauts actually feel congested all the time, almost as if they have a cold. So practically speaking, this translates to needing food to be more flavorful, savory, spicy, because otherwise it's just bland and astronauts won't want to eat it. So actually a fun fact is as of yesterday, or Halloween, the first chilies were grown and harvested in space and used in space tacos. And the other part of fluid shift is because your fluid's shifting upwards, your heart interprets this, the baroreceptors in your heart interpret this as an increased fluid load, and astronauts are actually excreting more fluid by urination for the first few days on station, actually leading to a partially dehydrated state. And there's more. And so we've talked about various fluid shifts. We haven't yet talked about cerebrospinal fluid and how this is affected in the microgravity environment. So cerebrospinal fluid is that brain juice, that proteinaceous clear fluid that bathes our brains and spines and provides nutrients as well as washing away debris, providing some immune protection. And so what we know with CSF, and this is a relatively new finding in human spaceflight over the last 15 years, is the occurrence of what we call SANS, or the Space Adaptation Neuroocular Syndrome. And basically this translates to impaired CSF drainage from the brain, particularly with increased pressure around the optic nerves as they exit the backs of the eyeballs. And we see this in long duration spaceflight over 30 days. And in some cases, even impacting the vision of astronauts, resulting in hyperopia. And very interestingly, for reasons we don't know, this is a male preponderance. So we see male astronauts develop this. When we talk about gender differences amongst astronauts, on the flip side, we see that female astronauts are more prone to the orthostatic hypotensive state. They're more prone to bladder infections, UTIs, because of the shorter distance at the shorter anatomy of the urethra. Overall, when we look at cognition and performance, we see no differences between male and female astronauts. And we're still learning. So this is the famous NASA twins study. This is identical twins, Navy pilots, astronauts, Scott and Mark Kelly. Scott Kelly spent 1 year in space. Mark Kelly was his control on the Earth. And this was one of the most collaborative interdisciplinary science investigations in human spaceflight to date, where they looked at the metabolomics, proteomics, genomics, macro level, cognition performance, the microbiome of Scott versus Mark. And it was really interesting because in some cases, changes were transient. There was this brain fog, this cognitive performance issues that Scott experienced that were transient and returned to pre-flight state after a few months on Earth. We found that the nature of his gut microbiome changed during flight, possibly as a consequence of eating space food and having an altered diet, but returned to his pre-flight status within 6 months of being on the ground. We even found immunological changes, and very interestingly, Scott Kelly was the first astronaut to administer a vaccine in space. He gave himself a flu shot in space during that mission to look at see if there's an adequate immune response. There was. And very surprisingly, telomeres, which as some of you know, the shortening of which is associated with increased aging, were found to lengthen during Scott Kelly's flight. So very interesting, comprehensive study. But wait, there's more. So as I said, despite decades of human spaceflight, the surprises keep coming. We're still learning. As recently as 2019, during a routine handheld ultrasound experiment on station where the astronauts were imaging the jugular veins of another astronaut, lo and behold, there was a giant clot or thrombus found in the internal jugular veins. And so then we have to suddenly ask, has this been happening all along? Is space a hyper or procoagulable state? Are we more prone to blood clots? And what does that mean for longer duration missions where we're further away from Earth? And so all of this is a primer to simply say that space is trying to kill you, if you remember nothing else from this part of the talk. And these are all lessons from low Earth orbit. And so we have to beg the question, what happens when we go beyond LEO? This isn't merely a theoretical question. We've sent humans to the moon last in 1972, and we have plans to go back. So as early as 2024, NASA has announced the advent of the Artemis missions to put the first woman and next man on the moon, and with a view towards establishing permanent surface operations on the moon by the end of the decade for science observation, Earth observation, sun observation, exploration, as well as serving as a way station and test bed on our way to Mars. And this starts with Lunar Gateway, the first space station in orbit around the moon, to be put in orbit, to construction to start next year, commissioned with crews as early as 2026, non-continuously crewed, again, science, exploration, and way station directive. And finally, we've talked a little bit about Artemis, but we haven't talked yet about the plan of using the moon as a test bed and springboard for Mars. And we'll talk a little bit about the distances involved in a few slides' time. So this is all to say that it isn't simply a theoretical question. There's actually plans between NASA, the Canadian Space Agency, the European Space Agency, and even the commercial space sector, for going to the moon and beyond. And as early as 2016, Elon Musk announced his plan to send humans to Mars by the 2030s. He said it may be a one-way mission. Hopefully you're okay with that. So let's talk a little bit now about the added challenges of going beyond low Earth orbit. So we know, despite having only 12 men walked on the moon, we know there's hundreds of pages of lessons from the documentation around what we saw in human physiology on the moon. We know that there was increased radiation, that lunar dust actually was turned out to be a skin irritant, a respiratory irritant, and actually clogged up the suit joints when they went on their moonwalks. And so for anyone who suggests that the moon landing was faked, well, they put a lot of effort into faking this whole moon landing. There are hundreds, if not thousands, of pages of documentation dedicated to research from the moon, the biomedical data that came from Apollo. And then the other part of this is the altered day-night cycle. So we talked about 16 sunrise sunset cycles on the ISS. When we get to the moon at the equator, the 16 days of day and 14 days of night as a day-night cycle. So let's talk a little bit about irradiation now. So the bottom line is the further out you go, the more radiation you're exposed to. And so at least at the level of the ISS, we're within the protective confines of the Earth Van Allen belt, so that higher energy radiation that we might experience from solar flares, or what we formally call solar particle events, as well as background galactic cosmic radiation, is mostly filtered out. It's why that we feel we're exposed to much less radiation here on Earth. A lot of it's filtered out through the magnetosphere. And so for comparison, from a numbers perspective, you're actually exposed to 250 times the amount of radiation in a single day at the level of the ISS than you would be on Earth. By comparison, 40 times in an airplane versus at ground level. And then by the time you're exposed, you're traveling to Mars, 700-fold versus one day on Earth. This translates to the equivalent of a full body CT scan every 5 to 6 days. And the travel time to Mars, depending on your launch window, is 6 to 9 months. And so then how does this, and this is higher energy radiation to boot, you're in deep space now. So how does this translate into physiological impacts? And so we know that different organ systems are more sensitive. So blood forming organs have a different radiation annual and 30-day limit than the eyes or skin. We know that there's gender differences. There's and limits for female versus male astronauts. And when we look at, for example, what history has shown us, we see that the annual limit for blood forming organs is 0.5 sieverts for radiation exposure. And then you look at what's happened in practice aboard Mir with the Russians. They actually exceeded that limit, that annual limit, during the one-year mission aboard Mir. And so that's simply 1 year. If we're talking about Mars, we can fully expect the mission profile to extend to several years, given how long it takes to get there. So speaking of distances, 6 to 9 months, what does that mean in terms of communication delays? So when we're talking about the moon, let's talk about ISS first. At the level of 450 kilometers altitude, traveling at speed of light, telecommunication delays are in real time. There's no delay. When you talk about the distance between the moon, this is 2.4 seconds round trip on average. So it's a little bit noticeable, but it's still possible to hold a conversation in real time. If there's a medical emergency, you can certainly radio back to Earth for help and actually be guided in near real time, for example, for performing CPR. Now, translating that 6 to 9 month distance with current propulsion technology, compare that to the speed of light. If you are the doctor on Mars and you have a medical emergency, say a mass hemorrhage or trauma or cardiac arrest, that round trip delay is now 6 to 46 minutes, depending on the conjunction of the two planets. So now if you have a mass hemorrhage, you do not have time to wait 46 minutes to have that round trip conversation. So when we talk about the challenges of human spaceflight as we go to the moon, Mars, and beyond, we summarize them as the big five. And so we've talked about them already: microgravity, and on top of that, we have 1/6 gravity on the moon, 0.38 gravity on Mars, distance from Earth, as we just talked about in the previous slides, radiation, isolation and confinement, which is also critical to address. What kind of personality does best in this type of environment, knowing that you don't have the creature comforts of petting your dog, talking to your loved ones, going out for a Starbucks, walking on the grass, as well as everything else which falls under hostile environments. So that includes what we talked about with those ultra day-night cycles, the rugged terrain on a moonwalk, lunar dust. So let's come back to our initial question. You are the crew doctor. What do you pack now? So now that I've adequately stressed you out on how space is trying to kill you, let's build up back our confidence a little bit, and let's talk about what tools we have at our disposal to prepare us for the spaceflight environment. So first of all, the number one tool is prevention. So this starts as early as selection. When we talk about the standards for becoming a governmental space agency astronaut, whether it's NASA, CSA, ESA, it's very strict. And so when we talk about reasons previous candidates have been selected out, I like to say that the pathway towards becoming an astronaut is littered with the hopes and dreams of medically disqualified candidates. People have been screened out for previous herniated discs, previous broken bones, anemia, which is reversible, color blindness, even a mango allergy, because there is known cross-reactivity to latex. You don't want to deal with anaphylaxis on Mars, just not ideal. It also deals with risk mitigation, so that's an extension of prevention. And so for the engineers in the audience, you can see a typical risk matrix. If something is high risk, high probability to happen, you need to mitigate it before you can proceed with the mission. So for example, we talked about decompression sickness and the oxygen pre-breathe prior to going on a spacewalk. The mitigation measure is that oxygen pre-breathe, so you decrease the risk of nitrogen coming out of solution. If something is high risk but very low likelihood, like performing a C-section in space, you don't worry about it, just don't send pregnant astronauts. And if something's low risk and high likelihood, like getting a trauma, lump, bump, or abrasion, you simply mitigate it. It continues, astronaut space health continues with rigorous pre-flight, in-flight, and post-flight rehab and countermeasures, which we'll talk about on the next slide. Nutrition, so we talked a little bit about how the nutrition and flavor and texture of food needs to change. In addition, it has to be lightweight, have a long shelf life. So oranges are a luxury because they're heavy, they're full of water, they don't have a long shelf life. They need to be nutritious, flavorful, and then you have to be able to prepare it without needing a stove, for example. There's a pre-flight quarantine, so NASA is doing it before COVID made it cool, as well as having an onboard chief medical officer, crew medical officer, so 40 hours of medical training and things like emergency dental procedures, starting an IV. and access to an onboard medical kit, medications, protocols, and access with mission control back on Earth. So here's a snapshot of what the checks or crew health care system looks like. And so we just talked about how prevention, monitoring are the primary mainstay of crew health. We talked about countermeasures a little bit. And then there's the health maintenance system. So countermeasures, let's talk about that a little bit more. So countermeasures include realizing that this environment is going to make you prone to muscle mass loss and bone density loss. So astronauts on station actually have to perform 1.5 to 2 hours of aerobic exercise and resistive exercise. So the advanced resistive ergonomic device, so a hydraulic system that lets them perform weightlifting like exercise. So 6 days of the week to counter that bone and mass loss, muscle mass loss effect. Here's a list of the medical equipment they have at their disposal. So advanced life support packs, basic life support packs, and then telemedicine capabilities, weekly consults with a flight surgeon, regular consults with the crew psychologist. The ground support team is very multidisciplinary. So you have flight surgeons. These are trained physicians who have aerospace medicine training that can come from all walks of training. So family medicine, there's urologists, neurologists, occupational health specialists, general internal medicine. You have psychologists. You have you're working with nutritionists, occupational health therapists. So it's very, very multidisciplinary. So we've talked about some of the prevention tools and the risk mitigation tools. Let's look at computer modeling tools when it comes to space medicine now. So here's a snapshot of the NASA integrated medical model. And so basically, this is a modeling tool that allows you to extrapolate what your crew medical kit should contain based on previous data of what has happened in spaceflight, assuming that you have the initial medical kit contents of what the International Space Station has now, and then you model that and extrapolate based on your proposed mission's crew size, duration of mission, and your acceptable limits for loss of crew life, as well as loss of mission. So you may be looking at this and saying, well, that's a bit one-dimensional. What happens if you have to use your antibiotics to treat a bladder infection, a skin infection, a respiratory infection, and then some other type of infection? So then you're actually depleting your medical kit, and that doesn't really account for the end limits that you've set for your acceptable loss of mission. So there's actually another tool called the Medical Extensible Dynamic Probability Risk Assessment Tool, which is why we call it the MedPrat, much easier to say. So this is a neural networking model based on Bayesian modeling that allows us to take into account different medical events, as well as different countermeasures at different time points in the mission to get several different end states and let us account for that. So now that we've talked about the tools, let's talk about what has previously happened in spaceflight and what we're preparing ourselves for. So this is the NASA Exploration Medical Capability top 100 list of medical conditions that the integrated medical model prepares us for. So everything from terrifying things like mass hemorrhage, mass trauma, cardiac arrest, to day-to-day things you can still expect to experience, like a congestion headache, to everyday things that are equally terrifying, but not life-threatening, like diarrhea in space. And here's a snapshot of what's actually previously happened based on space shuttle data. So we talked about the space adaptation syndrome, very, very common, nearly half of astronauts affected. And then everyday things. It's not the dramatic life-threatening things. It's not the urosepsis we saw in Apollo 13. It's more the skin infections, abrasions, lumps, bumps, constipation, GI distress. You'll see that behavioral signs and symptoms to make an appearance. Astronauts are human. They have a very rough, very tight operational schedule. It can get very stressful living and working in a confined space for months, up to a year at a time. And also, you need to be able to communicate that to mission control, as well as your crewmates, and also have a plan, for example, psychosis on the space station. And so one of the former chief medical officers at NASA's Johnson Space Center once famously quoted saying, there is a plan to deal with acute psychosis on space station, and one of those steps involves duct tape. So sometimes you have to MacGyver it a little bit. So now let's talk about the challenges of packing for space. How do we do that? When we talk about packing for space, we talk about the backpacking principle. So think of if you're going on a camping trip or a hiking trip, you can't bring it all with you. Everything that you bring with you comes at the expense of something else because you only have a finite volume of space to pack things with. You can, if you bring something, you may have to take something else out. So I like to refer to this as the Aladdin principle of space because it takes infinite cosmic power to get there, itty bitty living space. And so when we talk about the design challenges of packing for space, things we have to bring with us have to be low cost, low volume, low mass, low power, easy to use, radiation resistant, and have a long shelf life. They have to be able to withstand being in space. So we've talked a lot about all of these different factors to consider and different tools we have at our disposal. And so here's kind of a snapshot of what we all have to integrate. So from the human, the astronaut level up, we also have to think about the integration with the crew, the craft, the vehicle, the other crew members, the mission itself, taking into account that clinical aspect, the human performance aspect, the ergonomics, the engineering, and then we have to mitigate through training, contingencies, and emergency measures. So here's actually a snapshot of one of the medical kits they have on station, kind of really putting into practice everything we've discussed. They're highly modularized, they're compact, they're lightweight. They have medications to deal with the most likely common medical issues that will occur on station based on data. So antibiotics are common, painkillers are common, sleep aids are common. Maybe you won't find something to deal with, obstetrical care or labor because it's not, we mitigate that out by selecting out against pregnancy and space flight. So as we look forward to these exploration class missions, that is going to the moon, Mars, and beyond, the picture only gets more complex. So we're just talking about the tip of the iceberg when we talk about all these medical issues. Here is how long that laundry list of risks on the NASA Human Research Roadmap is. So this includes everything from risk of dust exposure on the moon to crew tensions and incompatibility to the risk of skills deterioration over the long course of a long duration mission to having a cardiac arrhythmia. It's a very long list. So the bottom line from this section is space is hard, space is expensive, and space is trying to kill us. So next question, how do we prepare for this hard, expensive, high risk, trying to kill us environment? Well, here's another question. What do the International Space Station, a remote village in Kenya, an Arctic or Antarctic medical deployment, and one of the world's only underwater research facilities, Aquarius Reef Base, have in common? So all of these are examples of remote and resource limited environments, and all of them, other than the ISS, because that is space, replicate the space flight environment in some way. And so because they're analogous to space, we call them analog environments. So in this next section, I'm going to take you through some of the lessons learned and how we prepare ourselves in extreme and analog environments based on some of the work and training that I've done. So let's start firstly talking about micro and partial gravity. And so you can actually replicate microgravity without ever going to space. And we do this through parabolic flight, what you may have heard of as the vomit comet. So if you can imagine, you have a traditional aircraft flying up and down in parabolas, and you're falling at the same rate as the airplane. And so if you think about if you're at the top of a roller coaster about to go over the peak of the roller coaster, you're weightless for a second, your stomach lifts up into your chest because you're falling at the same rate as the roller coaster. And the parabolic flight operates in the same way. And so you're falling at the same rate as the airplane. You generate 20 to 30 seconds of microgravity at a time, which gives you time to perform scientific experiment, test out new protocols and technologies. And what we've done through the International Institute for Astronautical Sciences, for which I'm a part of, and the Direct Space Medicine Group, is over 6 campaigns since 2015. We've tested an IVA or intravehicular activity spacesuit from Final Frontier Design. This is the spacesuit that you see. So we've been testing it to make sure to increase its technology readiness level, or TRL. So this is really important in spaceflight when we talk about technology development. So TRL 1 through 9 are the potential levels of technology readiness. TRL is concept phase, maybe something you scrawled on the back of a napkin in a bar. TRL 9 is spaceflight worthy, and so we've helped advance the level of this from TRL 5 through 6. And so I can keep telling you about what it's like, but I'd rather show you. So here's a quick clip from one of our previous campaigns that I'm just going to play for you. Oh, it's not playing. Let's try that again. It may not play because I'm on a firewall in my clinic, so that's okay. The video will be in the slides later. So what I did want to say about this is we're not flying at the level of space. We're flying at 17 to 19,000 feet when we fly parabolic flight campaigns. By comparison, a transatlantic flight flies 38 to 39,000 feet. So we're actually not even flying as high as a commercial airliner. Other ways that we can replicate partial gravity is through gravity offset. And so here is an example of a gravity offset harness that we tested at the Canadian Space Agency. In this particular scenario, we're testing the Final Frontier Design EVA, or Extravehicular Activity Spacesuit. You're quickly learning that exploration in space is full of acronyms. And so an EVA spacesuit has added layers of protection against radiation, thermal control, and is the kind of spacesuit you'll see on spacewalks outside the ISS, on the moon. And what this gravity offset harness allows us to do is offload a specified amount of weight from, say, 1%, which is negligible, to near 100% to simulate microgravity. So in this case, we're simulating microgravity, and I'm simulating fixing a panel outside of the International Space Station. We've also managed to offload 83% of our weight to simulate lunar gravity and test geological tools, as well as simulate 0.38 or 38% gravity to simulate Martian gravity. When we also talk about altered gravity environments, we can't neglect hypergravity. And so these are centrifuge studies I took part with at the NASTAR Centrifuge Center in Pennsylvania. And so basically, to get to that microgravity state, you need to accelerate quite a bit to get to either space in the case of space flight, or in the case of parabolic flight, you're accelerating upwards at 2 Gs before you can achieve that top of that parabola. And in this particular scenario, we were acting as test subjects for suborbital flight, which we'll talk about at the very end, basically seeing how does your average human handle a 6G load when it's front to back? And the answer is fine, although it becomes a little bit hard to breathe, and there's special breathing techniques to work around that. Elsewhere in the world of analogs, we talk about water analogs and what we can learn from them. So here is a snapshot from 2018 testing with survival systems when we were testing emergency egress operations. And so, for example, if that capsule, a simulated Orion capsule behind you, you see that over my right shoulder, necessitates an emergency, you have to egress into your emergency raft in the ocean that you see over my left shoulder. And you have to do so in your IVA suit. How does that suit integrate with the water? Is it watertight? How is it maneuverable? In fact, actually, I should have updated this slide deck because we replicated these tests in Groton, Connecticut just earlier, like 3 weeks ago. And we also created another water analog called the Neutral Buoyancy Lab. So you may have heard of this through NASA. They have a 6 million gallon swimming pool where they have recreated an entire mock-up of the International Space Station, and astronauts suit up in their EVA spacesuits and perform 8 to 12 hours of underwater work to simulate working in microgravity. We created one at Survival Systems as well, where we simulated needing to replicate and fix something on a spacewalk. And so we're egressing from our module, going to fix this faulty electrical system, and going back and working in weightlessness. And it's this incredible experience. So I'll try to find some slides that maybe we can showcase at the beginning of next class. We also talked about underwater research facilities. So this is yet another acronym. This is the Neptune Aquanaut mission I took part in 2019, the nautical experiments in physiology, technology, and underwater exploration. Myself and 4 other Aquanaut crewmates lived and worked underwater for 5 days, performing technology demonstrations, physiology, psychological testing, and in fact, you saw this make an appearance last class. So here is the Sievert radiology suite that I talked about that we worked on developing through Luxonic. We, in this particular scenario, I was liaising with the head of radiology in Saskatoon, Canada, over 4,400 kilometers away. And we met in this virtual space to review a complex fracture of a simulated trauma patient. And the idea is if you're on the moon, you have a fracture, you want to know how to set it, you can meet virtually with mission control on Earth and just get some advice or, say, what am I seeing here? And as you may be thinking already, there's some applications for Earth, which we'll talk about a little bit later. Elsewhere in the world of underwater analogs, you may have heard of the Aquarius Reef Base, otherwise known as NEMO, NASA Extreme Environment Mission Operations, where NASA astronauts live and work in underwater for 8 to 16 days at a time. So for comparison, Aquarius is only 13 miles distant from the Jules Undersea Lodge where we ran the Neptune mission, but the depth is what matters. So we were underwater for at 22 feet for 5 days. That's essentially surface pressure for the scuba divers out there. There's no decompression time. So you're technically in saturation because you've been underwater breathing the ambient temperature for 24 hours. At Aquarius Reef Base, you are at 63 feet underwater. And so then that atmospheric pressure makes a difference because now you're in saturation after 24 hours. And to safely decompress, you need to decompress for 16 hours and 47 minutes before you safely surface. Otherwise, you risk a dive injury and a gas embolism that, again, can, as we discussed earlier with decompression illness, can lodge in a bad place, causing joint pain, or in worst case scenarios, pulmonary embolisms, seizures, coma, death. So that's bad. And my favorite fact about this and the value of this analog for NASA astronauts is that by comparison, if you're on the International Space Station and you have an emergency necessitating immediate evacuation, you can escape from the ISS on your Soyuz capsule and get definitive medical care in Kazakhstan in as little as 3.5 hours. So you're actually more remote being under 63 feet of water than you are on the International Space Station, which is why it's such a valuable analog. So let's talk about another type of analog, isolated and confined environments, Mars analog. So this is the Mars Desert Research Station. It looks like Tatooine, but it's real life on fake Mars in the Utah desert, several hours outside, or just outside of Hanksville, USA. And basically, you are living and working as if you're on Mars. If you're going outside on exploratory activities, you're suiting up in a simulated spacesuit, lest the environment kill you, and you're bringing your science, your exploration, your crew operations with you. It really is a good lesson in crew dynamics. Lunar analogs, and so we saw a little bit of a lunar analog with the gravity offset testing and using geologic tools in a simulated geology EVA. You can also do so with geological formation. So here's a picture of a planetary geology course that we ran through IIAS in Flagstaff, Arizona. This is where the NASA, this is at Cinder Lake. So this is where NASA astronauts, as well as the Apollo astronauts, did their geological training. And then in the San Francisco volcanic flats, just close by, also in Arizona, we took these same tools that we took from traditional Earth planetary geological excursions, and then we adapted them based on lessons learned from Apollo, as well as lessons learned from EVA suits to make them more ergonomic for performing geologic work on the moon. And so, for example, this is the tool that I designed. And so when we talk about physical properties and gauging samples that we may want to collect, one of those properties is hardness. And you detect the hardness of a rock by using Mohs hardness scale, as well as tools that have varying softness and sharpness. One will be something like talc, very soft, you can scratch it with a fingernail, 10 diamond hard. and then using that to determine the properties of what you may see in the field and see if it's worth collecting. And so in this particular case, we created a tool that you can't carry necessarily a simple sharp pencil-like object in the field on the moon because it's really hard in those gloves, and if you drop it, it's gone. So we adapted this tool that I'm holding in my hands to have multiple prongs to be able to just rotate it with the handle. So if you're not very mobile, not very able to bend down in an EVA suit, you still have access to those physical properties. And to give you a more concrete example of why this might be useful, it might be easy to say, well, you're in 1/6 gravity. Why not just bring all the rocks because they're not that heavy? You also want to know what is of scientific value. So in 2017, the Mars Reconnaissance Orbiter found one of the probes in orbit around Mars found evidence of previous existence of deep sea hydrothermal vents on Mars in the Eridania Basin. So why does that matter? Well, we have deep sea hydrothermal vents on Earth, and we know that they're so hostile. They're kilometers underwater. There's no sunlight penetration. There's lit by these vents that excrete noxious chemicals and extreme heat. But we have seen life form in these extreme conditions where we didn't think life was possible, and we call them extremophiles and thermophiles. And so if we know that there's life around deep sea hydrothermal vents on Earth, and we know that there were once deep sea hydrothermal vents on Mars, doesn't it make sense to send exploratory missions there, and then also look for geological evidence to prove that this really does look like a deep sea hydrothermal vent? And so we know that serpentite is a example of one of the geological samples we may find around a deep sea hydrothermal vent, and there's strong evidence, spectrometry evidence from the Mars Reconnaissance Orbiter that may also be present at these deep sea hydrothermal vents on Mars. And so now, translating back to this, how do we determine which sample is serpentinite on a Martian EVA? Hardness is one of those properties that you can use. And so in the field, you can use this tool, say, is this the right hardness? This is an interesting sample, bring it back. So continuing onwards, other examples of analog environments, operational environments. And so you don't need to be resource limited, you don't need to be remote. You also want to work on the crew dynamics. And so here's a high altitude science campaign we ran around Nautilus clouds in high-level Alberta. We were testing a brand new tomography instrument that you see over my right shoulder, and we want to get more imagery and more data around the three-dimensional structure of these clouds. And so we actually had one tomography instrument in our aircraft and then two on the ground 200 kilometers apart to triangulate more three-dimensional structures. And we were working in this very small, tightly knit crew. There was the mission specialist, myself as payload specialist, and the research pilot, and we were constantly optimizing our communication to meet the mission objectives. Resource limited environments. So again, you don't need to go to Antarctica, you don't need to go to the bottom of the sea. You can simply simulate a resource environment. Here's a snapshot from the operational space medicine course I teach with IIAS, and basically we take non-medical professionals and we teach them the principles of wilderness triage, assessment, triage, and treatment. And basically put them through increasingly difficult scenarios from simple trauma, mass trauma, polytrauma, mass casualty night scenarios with a little bit of space medicine thrown in for fun. So we turn them into space medical MacGyvers. And the really interesting part about this class is folks with no medical training. We had search and rescue pilots, we had software developers. By the end of this course, they were performing amazingly at teams. They were getting through really difficult scenarios really, really well. And so here's also just a snapshot of an interesting paper is that we can't forget about the medicine and the safety in any of these extreme environments. And so here is a paper published by several colleagues and friends of mine on the standards and guidelines for extreme environments in space-like environments on Earth. Which brings us to a question as we enter the next section of this talk. When we talk about keeping humans not just surviving, but thriving on Mars and beyond, what is the gold standard? If we had no constraints, the answer would simply be to bring another Earth with us. If we could terraform Mars, well, then we would have 1G, we would have an atmosphere, we could filter out some radiation, have a magnetosphere. That would be really nice. But as we've discussed, we have a few constraints. So now we need to be a little bit crafty and innovative and resourceful when we talk about meeting the challenges for Mars and beyond. So let's ask a bit of a different question. What if we could not just provide the standard of care on Mars? What if we surpassed it? How do we do that? What if we looked through forward-thinking, emerging technologies and science fiction for inspiration? So what if we could overcome the bone density and muscle mass deterioration problem by providing gravity, by providing a partial gravity rotating space station, just like we see in Space Odyssey 2001? What if we could equip decompensated astronauts with a exoskeleton so they could still perform meaningful work on the surface of Mars? What if we just said 6 to 9 months is way too long? What if we could teleport humans to Mars? When it comes to skills deterioration, what if we could simply upload skills to our brains, just like in the Matrix? And what if we just said, well, that's all too expensive and too high risk. Let's just send avatars to Mars. So here's actually a look at what's happening in the world of research today and how that may equip us for exploration class missions. So I teased you a little bit with this snapshot from last class and a few slides ago. We talked about skills and virtual reality for both maintaining skills as well as providing medical modalities on distant surfaces or on distant planets. And so we talked about the Sievert suite a little bit. So here's now a little bit of a video of what exactly that entails and how that meets those mass volume power restrictions that we talked about earlier. It occurs to me that this video may not play, which is fine, that will be in the slides. Up there. Get back into this. Okay, so these videos will be available. And so we talked about technology readiness levels and TRLs a little bit earlier. And so we've actually brought this radiological suite to not just underwater, but in microgravity through parabolic flight as well. And so this is actually all in the same week in 2019. It was a pretty good week for virtual reality testing. So let's talk a little bit about the skills, maintenance, and deterioration. So imagine you're the crew medical officer, and the first time you learn how to put an IV in is on Earth in 1G training, and then you're not called to practice that skill until you're on the surface of Mars at least 9 months later. You're probably going to be rusty, and your patient is going to be looking like a pin cushion. So what if you could practice those skills in virtual reality? So you don't have to bring a dummy, you don't have to bring a simulation center with you. You could simply go through the practice in VR. And so this is actually a snapshot from a module that we've been funded and that we've developed for the Canadian Space Agency, doing exactly that. You're in deep space, you have medical procedures to practice, and you're able to maintain those skills in VR. And so that video will be available to you, again, with the slides. And so let's look elsewhere to inspiration from science fiction. Here's a snapshot of one of my favorite articles from the MIT Technology Review from 2017 that invokes some aspects of Gattaca. I'm dating myself a little bit with this 1996 movie, I think it was, where they genetically augment and enhance humans. And so this piece, futuristic looking, because they argue that perhaps it's ethically questionable to send humans as they are into this high radiation, high risk environment. So why not genetically select for humans that have more muscle mass and don't lose muscle mass as easily? Why not splice in human genes with elephant genes, not to generate space elephant man, but because elephants don't get cancer. And that's because they have multiple copies of oncogenes and tumor editing genes. And so what if we could splice that into humans to make them more cancer resistant? Well, that's actually happening today. So here's a snapshot from the Rodent Research 19 experiment that returned from ISS in September 2020. And basically they took jacked up little genetically engineered mice, that's this muscular mouse you see on the left here, and flew them with non-genetically engineered mice They compared them to non-flown mice, and they also introduced something called the ACVR2 neuromuscular blockade, which prevented bone density and muscle mass loss. And what they found was that these genetically engineered mice with the neuromuscular blockade tended to have less bone density loss, and in some cases even had increased muscle mass. So NASA is literally engineering mighty mouse. Elsewhere in the realm of science fiction, so what we talked a little bit at a high level about engineering, genetic engineering, and gene synthesis. And so this throws back to one of the themes we talked about when we talked about the 5 Ps of medicine, precision medicine, last class. And so part of it is gene augmentation using technologies like CRISPR to splice, for example, those elephant genes that we talked about, to looking at the constraints of the environment and developing things like point of care diagnostics for in situ blood testing, for example. There's all sorts of lessons from genomics. So there's a whole host of questions when it comes to pharmacodynamics and pharmacokinetics and how that's affected in the microgravity high radiation environment and the shelf life of medications in space. And if we know that the shelf life of a particular medication is only 3 months, maybe it makes more sense to use technologies like 3D printing to manufacture those medications in situ. And 3D printing is already in space, is already happening. Made in Space was the first company to put a 3D printer on station. They successfully printed a decade ago. So from a medical perspective, what if we could print the medical tools as well as have bioprinters to print organs for medical events on Mars, for example. Borrowing from science fiction, so 2 very famous examples of AI. So you see TARS from Interstellar and HAL from Space Odyssey 2001. But what if we apply machine learning and AI to diagnostics? Because remember, on any crew on Mars, you're going to have something on the spectrum to a crew medical officer with maybe X hours of training, to a crew physician. But what happens if the crew physician is the one who's incapacitated? Or the other part of it is physicians are only human. We are trained to know so much. We don't know it all. Part of our job is knowing what tools are at our disposal for diagnostics and decision making. So what if we can help with treatment and decision making algorithms through machine learning? We talked a little bit about generating partial gravity through a rotating space station, like we see in Space Odyssey 2001. So basically, the physics of it works like this: gravity is a function of the rate of rotation as well as the radius of your station. Here's a snapshot from a company that, in full disclosure, I'm the medical director of research for. So this is Orbital Assembly Corporation. We are working to build the world's first commercial rotating partial gravity space station. And how about what are the benefits of that? So on a long duration mission to Mars, for example, suddenly you don't have to worry about that bone density loss, that muscle mass loss, that space adaptation neuroocular syndrome if you provide the right amount of gravity. 6 to 9 months is a long time to spend in transit. So what if you could just sleep that time away in transit to Mars? And so there's people out there working on this. The European Space Agency studied human hibernation and published a report in 2019 saying that if you simply woke the astronauts up 3 weeks prior to reaching the surface of the red institutes working on this right now. So one example is the Alaska Arctic Biology Institute. They're looking at inducing hibernation in non-hibernating species. Why? Because the ground squirrel, which is a hibernating species, slows its metabolism down by 99% when it's in hibernation. Less metabolism exertion, less resource utilization. So they've actually managed to induce hibernation in rats, which don't hibernate successfully, with the small caveat of there are some side effects, including gut ischemia, perforation, sepsis, and death. So they still have some things to sort out. We talked about earlier, why can't we just teleport to Mars? Well, we're not close to that, but some people have asked, well, why can't we just get a faster engine? So here's a concept for the Vasmer plasma engine, pioneered by former NASA astronaut Frank Chang Diaz, saying with the right engine, the plasma engine, you could get to Mars in 39 days. Well, that's pretty much way more agreeable than a 9-month transit to Mars, and also mitigates all of that bone deterioration, muscle deterioration, fluid shift, as well as the boredom and skill loss that you may expect on a longer mission. So the bottom line is, if we're serious about exploration class missions, we are going to have to science the space out of this with a little bit of space MacGyvering as well. So in the last 20 minutes here, let's talk about what's next on the horizon of space medicine. So I just alluded to this a few slides ago. Having partial gravity would be great. How much partial gravity remains to be determined? So we still need to determine the gravity prescription. How much gravity for what duration, for what frequency, over what time frame is enough? We alluded to this a little bit earlier on about the psychological profile of a crew for Mars. And so we know that during astronaut selection, there are select in and select out criteria. You want someone who is both very team-oriented, mission-oriented, as well as able to, work as an introvert and work in solo. And there's actually research around the types of personalities that thrive in these ice or isolation and confined environments. And so resilience, it turns out, is a huge part of this. And it can be a learned trait that comes down to 5 key components: breaking things down, positive self-talk, mental rehearsal, impulse control, positive self-support. And we call this type of rising to the occasion in adversity salutogenesis. So that's the positive psychology term for that. And there's also research around coping in austere environments, and it's very similar to the research around resilience. And so there's planful problem solving. So there's that breaking things down, seeking social supports, just as in resilience we saw relying on our source support networks, enduring harsh conditions. There's that impulse control, emphasizing the positive. So that's that positive self-talk. And then the addition of relying on luck. And so if you're interested, I've actually published a book chapter on the subject called Psychosocial Resilience in Long Duration Spaceflight. And there's tons of research around the type of personnel who thrive in Antarctic deployment or on a submarine for months or in space. So if we're talking about mental health, let's also talk about other forward-looking questions. Well, what makes an austere environment austere? It's the lack of earthly creature comforts. So what if we brought those creature comforts back? What if we made spaceflight a little less austere? What if we brought pets with us to Mars? Maybe the morale, the boost, the trade-off is worth the resource consumption and the extra life support utilization. That would be a very interesting trade-off study to look at. Then you'd also have to factor in the impact on crew morale in the event of the passing of a space pet. Because scientists will answer any question, in case you've wondered what a bird will do in 0G, I've also included a video of what pigeons on parabolic flight, pigeons in 0G. I don't think the video will play, but it is worth every minute of the 44 seconds. Okay, so let's go back to the medical side. Let's ask other questions. So you're the crew physician. You are suddenly incapacitated. Say you are walking around and you feel this pain in your right lower quadrant and it won't go away and it won't get better despite everything you've tried walking it off, antibiotics. And before long you realize, oh no, that's my appendix. I have appendicitis on Mars. That has happened. This is a snapshot of, let's go back to that. This is a snapshot of Antarctic physician Leonid Rogozov and Soviet physician in Antarctica in 1961. He had that exact scenario, and before long he realized, well, I'm either going to die of a perforated appendix or I have to take my own appendix out. Spoiler alert, he took his own appendix out, he survived. So this begs the question, how do we mitigate that for Mars. And there's actually a paper out there published in 2012 by some famous flight surgeon names at NASA on prophylactic surgery prior to a long duration spaceflight. Is it worth the risk? There is also precedent for this. So here is a snapshot of Villa Las Estrellas, a Chilean settlement in Antarctica, very, very remote. It's on King George Island, 80 to 150 people, depending on whether it's winter or summer. And the rule is, as of 2018, because they're so far from definitive care, if you're age 6 or over, you have to have your appendix out in order to live there. So this isn't just pie in the sky stuff we're talking about. There's precedent for this on Earth. So let's talk about other challenges that we need to overcome before we can successfully talk about sending humans to Mars. We talked about the radiation problem earlier, and so we didn't really mention the mitigation. So that includes radiation shielding in transit when you're in deep space. That may include genetic enhancement for having more copies of oncogenes. And it also definitely involves engineering our habitats to be radiation resistant. And there are some who posit that there's no amount of shielding that meets our mass and volume constraints other than living and working under meters of regolith underground on Mars. We talked a little bit earlier, switching to other problems in exploration class missions, we talked about nutrition and how it needs to be lightweight, have a long shelf life, be something that astronauts will eat. So this is a even more compounded problem when we talk about a 3 to 5 year mission profile for Mars. So again, full disclosure, I'm a medical advisor to this company. This is a snapshot of Astrius, which proposes to exactly that. Provide a lightweight, long duration, nutritious confectionery that has vitamin as well as nootropics in it to enhance performance. Other questions as we get into the last 10 minutes is, if we're going to the moon or Mars to perform a different type of activity, we're still performing spacewalks, but now in a rugged, dusty, rocky terrain, our activities are changing. How does the nature of our medical capabilities need to change, and how do our medical kit contents need to change along with that? And then how do we build up those medical capabilities if we're serious about creating and maintaining a permanent off-world human presence? And so it's been done before. We've built up medical capabilities before. So what models can we look at from Earth, for example, from refugee medical establishments to military medical establishments to ISS models to inform these medical structures? And in what order do we build them up? So here is kind of the feelings on the topic and how we go from ISS capabilities, where your mission is to stabilize and evacuate to Earth, to where you don't have the option of evacuating. So then you have to go from basic life support to advanced life support to having a basic surgical suite, ICU capabilities, and then also building in that prevention foundation. And so there may be a point where we're going to do a routine colonoscopy on the moon. We're also going to train up the personnel in tandem, as well as provide the support and imaging capabilities in tandem, while respecting the constraints of mass, power, volume in conjunction with that. So we also have to ask ourselves, how are we going to plan the trauma bay of the future? And then how do we plan for those harder questions of what happens if you have to perform CPR on Mars? And there's actually papers out there on that. Here's a snapshot of the European Society for Aerospace Medicine. They published last year the most definitive guidelines on CPR in space to date. And there are actually methods for providing as effective as possible chest compressions in 0G. But you also have to ask yourself the question of, say you get return of spontaneous circulation. Well, where's your life support to support that? Now you may have just performed an exercise in futility. So we also need to develop the medical infrastructure as well as the ethics around it, because maybe the ethical, if you can't get life support once you get a pulse back, maybe you have to, the ethical move here is to not perform CPR on a downed crewmate. Other questions we should ask, we can't get away without asking in the COVID era, what happens if COVID comes to the moon? How are we going to handle the first moondemic? Knowing that gravity is 1/6 of what it is on Earth, are we going to have to socially distance to 36 feet on the moon? And if we're serious about establishing permanent off-world settlements of humans, just as Elon Musk proposes, well, then we have to talk about the space birds and the space bees and ask what happens if we want to give birth in an ultragravity environment, question mark, followed by 5 more question marks, because I've written a book chapter on the subject, and basically there are so many unknowns when it comes from everything from arousal to copulation to gamete development, implantation to in utero development, developing in utero to giving birth, to how that early childhood development occurs. And so the bottom line is we don't know. We don't know what the critical gravity dependent phases are, what the mechanisms and mutations are, and what the duration and intensity of minimum gravity exposure is needed. We have animal studies, we have insect studies, we have wasp studies, we have jellyfish and zebrafish studies, but the bottom line is we simply don't know. The data is conflicting at best when it comes to survivability and permanence of certain effects. If you're interested in this subject, I've included the reference to the book chapter that I've written, as well as a bit of a longer discussion on the challenges of pregnancy in space, including the support mechanisms, what can go wrong during delivery and prenatal care, as well as developmental considerations. And a bit of an ethical scenario, because you can't talk about development without talking about sexuality, is if we're talking about a human settlement on Mars, and say it's the first 6 humans to ever go to Mars, how are we going to design and plan around the privacy aspect, and what are the ethics, and what are the ethics about fraternization with other crew members? Can you actually dictate a policy against fraternization? Can you dictate a single gender crew? If you're taxpayer funded, do you have a duty to disclose if there's been liaisons between 2 crewmates who are married, but their spouses on Earth and were fraternized with each other? Do you mandate birth control? So this is a very fraught topic that we don't have time to get in depth into over the next 6 minutes that remain to us. But suffice to say that if we're serious about becoming a permanent off-world multiplanetary species, we should be looking at these questions yesterday. And of course, the most important question, if you give birth in space, would that baby be an illegal alien? So moving on as we get into the final minutes here, if we're serious about maintaining the standard of care, how do we enforce those standards? Do we need to evolve beyond having a World Health Organization with standards to having a galactic health organization? And if so, what form will that body take and how will it be governed? How do we train the doctors, the next generation of doctors? Do they need to have a specialty in Moon and Mars medicine? And what will that curriculum and training look like? And because humans are a very resourceful and resilient species, maybe all of those problems will prove a piece of cake for us. Then we should be asking, well, once we get to Mars and we survive and thrive there, where do we go to next? So let's bring it back home to Earth in the final minutes of this talk. So we talked about the governmental space agency, the formal space agency, exploration side of things. But this is also a very unique era in which to be alive. So what happens when we democratize access to space? This is happening right now. So in July of this year, both Virgin Galactic, led by Richard Branson, Blue Origin, led by Jeff Bezos, led civilian crews up in suborbital flight. In September of this year, we saw the inspiration for first all civilian crew fly up in a Dragon capsule, spend 3 days in an orbital mission, and they actually flew at a higher orbit than the ISS, so they've been further than humans have gone since the Apollo era. Here's a work that I've recently published on the subject with some colleagues on medical guidelines for commercial suborbital human spaceflight. And so it's very interesting because based on centrifuge and ground studies, spaceflight is actually pretty darn safe. It's just the duration of the flight profile. But if you're what we found from ground studies is that you can send humans age 18 to 89 with all manner of medical conditions, COPD, asthma, heart transplants, up. It's on a suborbital flight because that flight profile is minutes of 0G, and the probability of a medical event occurring in that flight period is actually comparable to commercial, a short duration commercial air travel. And so the most common reason someone would get disqualified from these studies that mimicked a suborbital flight profile was because they were anxious, claustrophobic, getting panicky, or just doing something unsafe. And so here's a resource from the New England Journal of Medicine called "Commercial Spaceflight in the Area era of commercial civilian spaceflight." And so I've included that resource if you want to learn more about kind of what's going on there. And then let's go one step further and say, okay, well, when we're talking about making space accessible, let's really make it accessible. So Stephen Hawking famously flew 0G with the 0G Corporation in parabolic flight in 2007. And then for a long time, nothing happened. And then this year, making history, the European Space Agency opened up an astronaut call, but also announced the call for the first ever para-astronauts. So specifically looking for humans with lower limb deficiencies, or a pronounced leg difference, basically people who had impaired usage of their lower limbs, because the theory is in 0G, it shouldn't make a difference. And in fact, coming back to the Inspiration 4 crew who flew earlier this year, Haley Arsenault is a physician's assistant and survivor of childhood cancer who became the first astronaut with a bioprosthetic in space. Just 2 weeks ago, Astro Access launched its parabolic flight campaign with Astro Access ambassadors. So these were a group of ambassadors who were either deaf, blind, or in some cases mobility restricted, paraplegic as well, and they successfully completed their 0G flight. So the frontier for spaceflight is opening up, and this really is the best time to be involved with space, because suddenly we're saying maybe spaceflight isn't just the domain of pilots and engineers and scientists, but it's for everyone, and the artists and the explorers, the entrepreneurs and the storytellers too. And so the final point I want to make is we talked a lot about the likenesses between remote, resource-limited, isolated environments. You may as well argue that it's easier to get medical care on the ISS than in Via Las Estrellas or the Aquarius Reef Base. And so what we know about these environments is that they're all resource-limited, but also excellent drivers of innovation. And so this is important because 44% as of 2019 of the world's population live rural. They don't have access to those major tertiary healthcare centers. So how do we use those lessons learned from space to make healthcare and life better on Earth? Well, here's examples of some technologies from space that have been used to make life on Earth better. So in the top left corner, there's iodine resin water filtration filters from the ISS that have been spun off to provide clean water to villages in Kenya. You can see handheld ultrasound in that middle top slide, used on the ISS, used to provide maternal and obstetrical care to remote Arctic populations. Space blankets provide warmth to disaster victims. Solar-powered refrigerators to refrigerate vaccines in areas with no electricity. Atmospheric scrubbers from portable life support systems used to clean up the atmosphere in transport to lengthen the shelf life of produce, and portable telecommunications. That was a whirlwind through the world of space medicine and emerging challenges and technologies. So we talked about the hazards, tools for helping mitigate risks, the challenges of packing for space, how we prepare for space through analog environments on Earth, emerging technologies, and emerging challenges. So that's all to say we're not going to solve any of these challenges anytime soon. We need all comers, all disciplines, all brains. We need you. And it seems like a lot, but all these problems start with dissecting them one step at a time. So thank you very much for your time. And I will turn it over to you for questions or comments now. Thanks very much. And looking forward to your comments.
Okay, any questions?
We're at time, so I realize people may have other commitments. So what I will simply say for next time is for today, if you're interested in extreme medicine, austere environment medicine, space medicine, I've included a lot of links. Kim, I owe you my slides from this time and last time, so I'll send those on once I'm
Great.
done today. And then I've recently delved into the world of space med tutorials. So a condensed version of this talk in tweet form, as well as some of my favorite resources, textbooks, papers on space medicine. I've included the links here as well. So you should be well prepared to join into the world of space medicine. Send me a message if you have questions. And thank you very much for your attention. Next time will be all about workshopping, working in small groups, and applying principles of exponential thinking. So thank you for your attention.
Sounds good. Okay, great. Thank you very much. See you next time.